All AI diffusion models explained. Let's start from the basics. Diffusion models generate data by gradually removing noise. Starting off the process is all random noise and reconstructs the image step by step, learning how to reverse corruption. Each step refines the output, moving from chaos to structure until a coherent, realistic image emerges. This stepwise approach allows the model to learn patterns, textures, and details without directly memorizing examples. By training on large data sets, it understands how data evolves from randomness to order. In essence, diffusion models turn noise into creation. They form the foundation for every modern AI image generator, from art tools to advanced research models, demonstrating how controlled randomness can produce highly realistic outputs. But what happens when this basic idea becomes a full working model? Next up, denoising diffusion probabilistic models, or DDPMs, were the first major breakthrough in modern diffusion. They apply probabilistic rules to denoising. Instead of simply reversing noise, the model calculates probabilities of what the clean data should look like at each step. The result is image generation with remarkable quality, capturing fine detail and realistic structure. DDPMs quickly proved that diffusion could rival and even surpass older generative models like GANs. But there's a catch. This process is slow. Generating a single image can require hundreds or thousands of denoising steps. High quality, yes, but at the cost of efficiency. DDPMs established the foundation, but their limitations opened the door for faster, more practical successors. So how do you speed things up without losing that sharp detail? Latent diffusion models, or LDMs, solved the efficiency problem by moving the process into a latent space. Instead of denoising huge pixel-by-pixel images, the model first compresses the image into a smaller abstract representation. Diffusion happens there, requiring far fewer steps before expanding the result back into full resolution. This shift cuts generation times drastically while keeping image quality impressively high. The most famous example is Stable Diffusion, the open-source model that unlocked powerful image generation for the public. With LDMs, diffusion left the research labs and hit mainstream use. They balanced speed, quality, and accessibility, showing that practical generative AI could be both fast and stunningly realistic. But what if you could actually tell the model what to create? That's where conditional diffusion models step in. Instead of generating random images, they work under guidance using text prompts, class labels, or features to steer the process. The noise removal still happens step by step, but now the model knows the direction it should go. This guidance is what powers models like Imagen from Google and Glide from OpenAI. You can type a phrase like, "a cat riding a skateboard," and the model denoises towards that exact concept. The result is controllable, highly specific outputs instead of abstract guesses. Conditional diffusion gave rise to today's explosion of creative AI tools, where users finally decide what the algorithm paints. But what if words alone were enough to shape entire digital worlds? That's the breakthrough of text-guided diffusion models. Instead of requiring labels or predefined features, these models listen directly to natural language. You type a sentence, "a castle floating in the clouds at sunset," and the model uses diffusion to translate text into matching images. The most famous examples are DALL-E 2 from OpenAI and Midjourney, which have transformed creative industries. Artists, designers, and casual users alike now have tools that respond to imagination instantly. The strength here is flexibility. Any idea can be turned into visuals, no coding required. This accessibility made diffusion go mainstream, turning AI art from niche experiments into global, everyday creative platforms. But what if diffusion could be reframed through pure mathematical gradients instead? And next up, that's the idea behind score-based models. Instead of directly removing noise step by step, these models learn the gradients of a data distribution, essentially mapping where the data is most likely to exist. By following these gradients, the system reconstructs realistic samples. Early versions like NCSN and its improved successor, NCSN v2, pioneered this approach. They showed that diffusion wasn't the only way forward. You could reach similar results through gradient-driven processes with strong theoretical underpinnings. The big advantage here is stability. Score-based models often produce smoother training and more reliable outputs. While less widely used commercially, they reshaped research by grounding generative AI in rigorous mathematical foundations. But what if diffusion became even stronger by merging with other AI tools? Speaking of, next we see the power of variational and hybrid diffusion models. Instead of relying only on noise removal, these models combine diffusion with VAEs, variational autoencoders, or transformers to boost performance. The result is systems that balance efficiency and quality in ways pure diffusion alone struggles to achieve. This hybrid approach shows up in advanced applications like image synthesis, video generation, and multimodal AI, where text, sound, and visuals all connect. By mixing strengths, the structure of VAEs, the sequence mastery of transformers, and the realism of diffusion, researchers unlock sharper, faster, and more versatile results. These models point to a future where diffusion isn't isolated, but fused into broader, more powerful AI ecosystems. And what if these models weren't theory at all, but everyday tools already? That's exactly where diffusion models shine today. Their most visible use is image generation, powering platforms that let anyone create artwork from prompts. They also handle editing tasks like in-painting missing details or transforming styles between paintings and photos. Beyond still images, diffusion is quickly moving into video generation, where short clips are synthesized frame by frame. Audio researchers are using the same principles for music and speech synthesis, while 3D designers explore diffusion-driven object and scene generation. This versatility shows that diffusion isn't just about novelty art. It's becoming a general-purpose creative backbone across industries, fueling design, entertainment, and research in ways traditional tools never could. What if the same power that excites us also hides serious flaws? You see, the diffusion models demand huge computational resources. We are talking training that requires massive GPUs and energy, which limits access to big companies or labs. They also inherit biases from their datasets, meaning generated outputs can unintentionally reflect stereotypes or misinformation. Another concern is the misuse potential. These systems can generate deepfakes, misleading visuals, or content that's difficult to control ethically. And that is even in normal use. Edge cases arise often, and sometimes the models produce distorted hands, inconsistent text, or they just fail to follow prompts exactly. These limitations remind us that diffusion models, despite their brilliance, are not perfect. They bring challenges of cost, trust, and responsibility that researchers and users must actively address as technology spreads. And the real question isn't just what diffusion models can create today. It's what boundaries are we allowing them to erase? Let us know what you think in the comments.